Greetings and welcome to Apogee Components RockSim Live. This is March 1st, 2024. Welcome everybody. And we'll just let me know if you can hear me and so forth. All right. Anyway, today I thought I'd bring everyone along on some more work that I'm doing kind of behind the scenes. I'm preparing. I'm on the wrong thing here. There we go. You can see me now. You saw the rocket that we're going to be talking about mostly today, but I'm preparing to do a new. I'm preparing an article for the Peak of Flight newsletter. Not sure when I'm going to get to it, but it's kind of an article in development. And the idea is I'm going to be comparing probably a half dozen, maybe more, flights of a rocket to simulations. And so parts of that come back to just generally dealing with designing a rocket, doing the simulations, and that sort of thing. Other pieces of it are going to be the later data analysis pieces. And so I'm going to kind of go through all of those chunks as I see them so far, and then we'll see where we end up today. Let's see. We've got Parker, Colorado. We've got Canada. Audio and video is working. Excellent. Yeah. Semi-frozen. You know, if memory serves, the last time I stood here, we were cold. Today is actually a pretty beautiful day here, so I'm glad about that. I am happy about that. Anyhow, let me move forward here. So what we have today is this guy. Now, these are not colors I am particularly fond of, so I have decided that this rocket is called the Eyesore, E-Y-E-S-O-R-E. It is not my idea of a beautiful rocket. However, this rocket is designed to fly on F-41s. It will easily go 3,000 feet and come very close to breaking the speed of sound. And that's entirely deliberate because I'm really interested in doing simulations and comparing them to flights in the transonic region. So that's like 0.8 Mach up to 1.2 Mach. And so this is a simple way of making a rocket capable of that isn't too expensive. So this is kind of, basically it's a cut down version of the Aspire, but it was just made with scrap parts. So this is the rocket that we're going to be going over today. And for the flights, I'm actually doing a couple of special things on the flights to make sure that I have good recordings of them. And also ensuring that I really, really want to get this rocket back because it's not going to be cheap. So the first thing, I'm flying a Blue Raven, and I don't know how many of you have seen these. They're tiny. They're tiny. This has 4 pyro channels on it. It also has 2 accelerometers and a gyroscope and all kinds of stuff. So that'll go in here. In addition, I'm going to fly a camera. Now this is, it's a RunCam split, and it's actually, you've got the camera over here, and then this is basically the recording. So you've got the little camera and then the board, and those will also fit in here. So I'm going to have a camera as well as the Blue Raven in there. As you can imagine, I want to get this back. This is not going to be cheap flights, and it'll be even more expensive if I have to keep replacing the electronics. But that gives me, what that gives me, the Blue Raven records 500 samples per second on all of its sensors. most of its sensors, I should say. And then the RunCam, this camera, records 4K video at 50 frames a second. So I'll have very nice video as well as lots of other data. And that will be very nice to use to compare against the simulations. So now if we go, let me see what else we got. We've got Arizona, Florida, nice. So now if we go to RockSim here, here is the eyesore in RockSim. And this is, for all intents and purposes, a very simple rocket. And I notice I forgot to change the color of this earlier, so might as well do that. So we can go into the launch lug, go to color, choose the diffuse color, and then just make it yellow with like the rest of that body tube. So what we have here, if I go to side view, what we have is one of our standard 29mm nose cones, a payload bay, and then a back tube. Very large motor mount tube here, which makes sense because when we go to the motor here and load it, you can see that the motor I'm planning on flying it on actually takes up a fair amount of that motor mount tube. Not all of it. I made a longer motor mount tube than was absolutely necessary just to help reinforce it. But it's a big motor in a small rocket. And then the streamer here, which is more difficult to select at this point. There we go. The streamer here. I don't have it in here in the rocket at the moment. Otherwise, I'd show it to you. But it's about a 5-inch wide, 6-foot long streamer, nylon streamer. Barely fits in the tube. But so that I can increase the chances of getting the rocket back, I have a big bright streamer. Actually, it's kind of a neon green, not this yellow exactly. Similar, but neon green, and then neon pink. So the colors are pretty consistent through the whole thing, if not all that attractive. But this is the rocket. It's a simple rocket. It's designed to be fairly rugged and fairly easy to build. I just want something that goes high and fast and holds the electronics that I wanted. And this fits the bill. So now what else? Potential on lost sound, but it sounds like maybe not. Okay, so question on describing the cut launch lugs in RockSim. So if I go back, come on. This is exactly what we're talking about. A nice slash cut on the launch lugs. How does RockSim handle it? It doesn't. It doesn't handle it from the standpoint of drag, nor does it handle it from the standpoint of just appearance. Now, if I open, one thing that I can do, that's the wrong one. There we go, we'll get there in a moment. So if we go to the Apogee website, we do actually have a newsletter article on the drag effects of slanted launch lugs. So if we go here, don't off the top of my head remember which one it is, so hopefully we can find it here. But basically what that article demonstrates is that, well, two things, I guess. One, there is an effect, and two, it's quite small. So it's not something to worry about from the standpoint of getting a decent simulation. It will change it, but it won't change it a lot. So launch lug. Using paper clips in place, standoff, aligning multiples. Of course, it's not going to be that easy. Let's try slant. New, lug. Same ones. Oh dear, it's always fun finding things. Well, I won't waste too much time finding it at this particular moment. It is, as I said, the two kind of takeaways of the article were that it does have an effect, not exactly the effect that you would expect, because for instance, this launch lug, this launch lug is cut at a slant front and back into a trapezoid, and the actual best drag design that Tim found was that both are slanted back and out, which is not necessarily what one would expect. But again, it was a very small percentage, under 5% difference in altitude, so it's fairly small. And if you just wanted to do the appearance, if you just wanted to make it look correct in RockSim, rather than using the launch lug itself, you could always just use, if we go to the tube, we could always just use a single fin. We just need one fin. This is using a 1/4 inch launch lug, so we could use 0.25 inches, and then the height, the semi-span that is, would be 0.25. And now we've got something very akin to, and we'll slide that into a different place. There we go. So now we can have something that's visually very akin to a slanted launch lug. And there we go. So that gives us the ability to get something that looks like a slanted launch lug. The drag of that, of course, will not be the same as the launch lug drag model, but it's a small price to pay if you're just looking for the appearance. So we will delete that. Oh, okay, we've got sound. Okay, so needing a launch or a ring, a centering ring, inside of a coupler tube. And what you can do is just manually enter the numbers. So here, this design actually has a tube coupler. And what I can do is add the centering ring. There we go. Sorry about that. We're on the correct screen now. And you missed all of my launch lug additions. Go figure. It's just one of those days, I guess. But the body tube, the payload tube, has a coupler at the back. And if I want to put a ring in this coupler, as stated, it won't allow me to add that. I can add it to this ring here. And so if I look at this tube coupler and open it up, the inner diameter is 1.08, roughly. But I will add a ring to this body tube instead. So now if I go and add a centering ring, I will make the outer diameter, I'll tell it not to automatically calculate, 1.08, and then the inner diameter well, we could just make this some random size. We'll make this 1.7, whatever. And then we can slide this wherever we want inside our coupler. And that is now a ring that is inside our coupler. So all of our mass properties will be correct. The drawing will look, the visual appearance of the drawing will be correct. All of that's correct. The only thing we've done is we've added it to a different component as the parent component. So that's the way we can add centering rings, for instance, inside a coupler. We'll delete that, and we'll delete this. Yes, delete. All right. All right. So I'm not actually sure on the external subassemblies, so I will not try to answer that incorrectly. I'll just leave that one for Tim at some point. And then a RockSim file for the Estes Super Neon XL, and no fins on the outer fin tubes, doesn't fly well in RockSim. So a question on that. In what way does it not fly well? So this rocket here, the eyesore, has a stability margin. It's very stable. And most of this comes from the fact that there's the weight of all the payload in the nose. But is it, for the Neon XL, is it primarily lack of stability, or is there something else going on? If it's lack of stability, then the lack of the fins on the outer tubes is very likely the issue. And that is definitely fixable. And we can talk about that. Until that, and feel free to clarify that. I'm going to move forward to the next thing I had for some of this other stuff. So basically, one of the things I wanted to do is to, oh dear, running out of time. Here we go. Here we go. One of the things I wanted to do is to actually compare the simulated coefficient of drag with a calculated coefficient of drag that I get from the flight. And of course, there's always the standard old-fashioned way of doing it, backing it out using RockSim, where you set the coefficient of drag, and then you run a simulation and you adjust up and down until you get a flight that is good, that matches the altitude you measured. However, one of the things that's important to realize is that coefficient of drag changes with velocity. So setting a singular coefficient of drag isn't all that accurate. Tumbles off the launcher. That's interesting. I'm not sure what that's about. Well, let's see. We also have, is it possible to design the bell-shaped motor retainer from Giant Leap rocketry? So the way you would do a bell shape is to combine transitions. Now, the back here is a transition. It's so close to cylindrical it doesn't look like it, but it does actually taper a tiny bit. But what you could do, let's put a better, more visible transition on here. So the front diameter, oh boy, cancel. I don't remember what the back diameter is. It's not that important though. That would be about 29 millimeters, 1.12. It's pretty close. Oh, we're just at the front. That would explain it. And then we'll go to, let's say, a 1/2 inch. And yes, it's at the front of our rocket. We need some length there, a 1/2 inch also. We don't need to save that. And then we'll put another transition. Cancel. The front will be a 1/2 inch. The length will make it 3/4 of an inch. And then we will make the back diameter bigger again. 3/4. And that'll give us, if we zoom in here, there we go. And that'll give us any kind of combined nozzle shape, bell shape that we want. And of course, any one of these transitions we can then change. Maybe I want that ogive or any of our other shapes here. So that allows you to do more interesting things. And to make the motor really, that's the nice thing, and it will have very minimal effect on anything. And sweep. Anyhow, there's our fin up outside of the body. So if you have any tubes in the middle, they're not attached to the tube fin on the outside, they're attached to the central tube on pods. And once you have one of these, you can just duplicate this. You can copy and paste it, and then go into the pod and change the radial location, and that'll put it just in a different position. And so that it just rotates down into the side. And you can get them in the correct location that you need for the rocket. So that would be the way. That'd be the way to add those in. Yes, alrighty. Let me go back, let's see. Launch visualizer, let's see, winds I put into the launch visualizer prior to launch are not the afterflight, let's see. Okay. So I am also not great. Oh, good. Now I have connectivity issues with chat. That's wonderful. Well, I will assume that we are still streaming. Let's see. So I'm not great with the launch visualizer. I'm not sure what the issue would be with the winds not showing correctly, or not, perhaps not being used correctly when they are previously assigned. So let's see, front camera. Oh my goodness. All right. So let's take a look at some stuff here. So basically, I decided one of the things that needs to be done is to calculate the coefficient of drag from actual flight data. And to make sure that that's working properly, the easy way to do it is to just use RockSim. We can export data from RockSim. We'll look at that in a moment, but let's look at what needs to be done to calculate it from the flight data. So the first piece is understanding Newton's first law, and that's easy. That's force is mass times acceleration. So we have a force, we have the mass of an object, and then we have the accelerations, the rate the object is being accelerated. So for the rocket, from the flight data, the force is going to be drag, the mass is the mass of the object, and the acceleration is how quickly the rocket is accelerating, or for us, decelerating, because the time to calculate the coefficient of drag is when the rocket is decelerating, when it's coasting. Then we also need to know what the drag is, obviously, if we're using that in Newton's first law. That's pretty simple. It's 1/2. This is rho. That's just the air density times the velocity squared times the coefficient of drag and times the reference area. So the reference area on the rocket is, boy, and I managed to do it again today. It's just not my day, is it? All right, here's our drag equation. So the reference area is the frontal area of the rocket, the largest diameter. That's the general frontal, or the reference area that's usually used. So then a little bit of arithmetic. We can solve for the coefficient of drag, just rearrange things, plug that back in Newton's first law. We get mass and acceleration here, and I've just corrected for gravity, because some of the acceleration isn't coming from drag, it's coming from gravity. So I correct that, and this is the equation that we're then needing to calculate. The mass that I'm going to use is the mass of the rocket empty, plus the mass of the casing, or just the empty motor, since I'm running this after the propellant. Okay, still am getting no chat, but I am also seeing the streaming, so we'll see what happens. Okay, we're back. I assume you can pick it up if it is going out on our end. So a comment that lost a lot. If it was making it out of the building in the freeze, then it should be on YouTube later. If it was an issue with the internet out of our building, then it will be gone in YouTube as well. So let's hope that it was somewhere further down the line. Okay. So the point being, we have a fairly simple equation that allows us to calculate the coefficient of drag. It's just the combination of the drag equation and Newton's first law and a little bit of arithmetic. Nothing too terribly difficult. So the question, though, is how do we use this? Because it's all fine and dandy to say you have this equation. Well, how do we do something with that? And the first thing that I like to do when I have the opportunity is to make the computer do the work for me. I would not say, and I'm not even going to say that I'm lazy. That's not even the issue. I make a lot of mistakes. I know that once I get the computer to do it, it's more likely to be right. So the first thing we need is some data to use. And we can get that directly from RockSim for testing. So I've run 6 flights, and you'll see that they're actually giving me different altitudes and things like that. So why is that happening is the first question. And that goes back to the question about the launch visualizer. That's the wind. So when I set this launch up, I set it up so that I actually have variable winds. There's some turbulence involved, so that each time that I run a new flight, I will get slightly different data. And this is not a whole lot. You can see the maximum altitude. What do we have here? The lowest altitude is 887 meters roughly, and the highest altitude is 893. So it's about 6 meters difference. So, you know, just around 20 feet difference. This is for a rocket that's going close to 3,000 feet. So that's not a lot of variation, but it is something. And this allows us to get multiple flights that we can test against. So once I've run these flights to actually export the data, I can select the flight, go up to File, Export, Simulation Data, and then in the file name, I will put just the name that I'm going to use. It's filled that in for me here, but every flight that you export, in my case, I exported 6. Every one I gave a different name so that I could use them separately later. And then what I did is I exported the time, the total acceleration, because we need the acceleration. I exported the velocity. I exported the altitude, which I don't need for calculating the coefficient of drag. That was nowhere in our equation, but I wanted to be able to just plot kind of the altitude versus time so that I could see the really basic flight. And then I also exported coefficient of drag so that I could compare what I estimate against what RockSim is using. So once I've selected all of that, I can just say, okay, export is completed, and now I can go to the desktop and just open that up and see what we got. Desktop. Unless I saved it somewhere else, which is highly likely given the number of slight issues today. No, it's supposed to be on the desktop. That's interesting. Let's go to the actual desktop. Open this up, desktop. There it is. It was right there. Okay. So this is what we got. Oh. And kinematic viscosity is automatically selected, and I just forgot to deselect it. Oh, fine, we'll open it up somewhere else. We'll open it in Google Docs, because they're not going to complain about it. So basically what RockSim gives us is just a basic CSV file, comma-separated value. So each of the values, as makes sense, is separated by a comma, and the file, and then each set of data is separated by a new line. So we can just go, come on. We are definitely having some internet issues here, so that is unfortunate. Go back to the desktop. You can see there's columns for each of the things that we selected. There's a column for time, for acceleration total, velocity, altitude, coefficient of drag, and then, as I said, kinematic viscosity that I just forgot to turn off. And this is all the data that we have. It's a lot of data. We've got a lot that we can work with. And of course, I exported 6 of these files. I've got 6 different flights. And the way I dealt with that, the way I processed that, let's see, where are we time-wise? Don't want to let it get too far away from me. All right, we're doing well. I'm using a service called CoCalc. I'm programming in Python because I like Python and it's easy. But the nice thing is, this is a free service. So you can sign up and have access to all of these systems, all of these libraries, and actually be able to share it. All of this stuff is freely available anyway. You can download it to your computer and run it there. But it's really nice that I can then do something like a presentation and use this online. So if we go to the Explorer, we can see I have 6 different flight files, and then I have this file here. This is called a Jupyter Notebook file. Doesn't matter. It's just a way to put some text and some code, different things together into a single file. And I'm not worried about the exact code today. I don't want to try to teach anybody Python. If you're interested in Python, let us know, because I could absolutely do articles about it. But it's not necessary for understanding what we're doing today. It's just a way to actually be able to visualize the data and do some of the processing. So the first thing I had to do was to import the data. And to run things in CoCalc, I just hit Shift-Enter. So I just ran this and imported some of the libraries. So what I did is I just looked in the file directory for anything that ended in .csv, and I said, well, I think that's probably what I want. That's one of my files. So this is just importing anything that ends in .csv. Okay. And then I want to find the time of Apogee. I want to find when it gets to Apogee, because I just want to look at drag, coefficient of drag during the coast time. And that is going to be between burnout, motor burnout, and Apogee. So I need to know when Apogee is. Basically what I did, I looked at argmax, just says, what's the biggest value? So Apogee is defined as the highest altitude. So I'm just saying, which of the values is the highest? Tell me which one that is, and I will just say that the time that I want, Apogee time, is the same index as that. And then I just store the index because I need it later. So you can see these are really consistent. It's 10.71, 10.6675, 10.68875. They're all very consistent, which we would expect. It's the same rocket flying on the same engine with just mild, small differences in the wind. Then here I'm just plotting the flights to Apogee. And the first plot, this is the altitude over time. And of course, I'm just going up to when we hit Apogee. This is not the descent again with the streamer. The reason that I do this plot is just as a sanity check, just to make sure that the data that I'm getting makes sense to me. And there are indeed 6 flights that are plotted here. This shows how very similar these flights are. I would not expect actual recorded real flights to be anywhere near this similar. Maybe I should have put more range on the wind in RockSim, but this is what we have. And then down here, the second of these plots, in the blue, we have acceleration, and in the green, we have velocity. And acceleration is shown on the right hand, or the left hand side here, and then the velocity is over here. But again, these are just sanity check sorts of things. Then we have reference values that I need to calculate things. We have the masses. So again, I used the total mass is the empty mass of the rocket, so just the rocket by itself, plus the empty mass of the motor. And the F-30 is basically 30 grams empty, and so these are in kilograms. And the rocket itself is about 108 grams empty. AREF, this is kind of an unfortunate thing because I'm working in standard metric units. This is the frontal area of the rocket in square meters. A meter is really big for a model rocket, so this number ends up being very, very small. But that's just a 29 millimeter body tube. What's the area of that circle? This is the time to burn out the motor. Again, the F41W, that's a Quest, fairly new Quest motor. It burns for 1.1 seconds. The density of the air, which is 1.2 roughly kilograms per cubic meter, and then gravity 9.81 meters per second. So these are all just constants that we need to calculate things later. Then I need to calculate and plot the coefficient of drag. And there's a number of steps that I need to do that. I need to figure out what index the burnout happens on. This isn't something that I would need to do with the RockSim files because it's going to burn out at the same time on every single file because that's how the simulation works. But this is a step that I may need to do on recorded flights because it may or may not, many altimeters, including the Blue Raven that I'm planning on using, will have some samples before liftoff. So this just says step through it until it's after 1.1 seconds, and that's when we start paying attention to it. And it just tells me what those indices are. This is just, here, our calculate the coefficient of drag. This is just the formula we came up with here. It's just taking the acceleration and the velocity and using those along with the mass and the gravity. The S is the frontal area, and rho, the density, just takes those, uses them to calculate it. I just made a function here to simplify things later. Then I had the data for the whole flight. All I want is the coast period. I want from burnout, so I have an index for burnout, and then I have an index for apogee. And this -50 just says, don't quite go to apogee because the velocity at apogee goes to 0, and that is on the bottom, and then you have division by 0. And yeah, that doesn't work. So we're going a little bit before.